All right, welcome to the second part of the 4-6 notes. Where the last video left off was right here with Theorem 4-6, the hypotenuse leg theorem. This is something that only works with right triangles. You have to have two right triangles in order to use it. What it's going to say is as long as you have both pairs of hypotenuse congruent, that's the longest side of the triangle, congruent to each other, and then one pair of legs congruent, that's either leg, and then like we already said, as long as it is a right triangle, there's a right angle there, that means we can use the hypotenuse leg theorem to say the triangles have to be congruent. So if you are wondering if you can or cannot use it, you need to check three things. Are they both right triangles? Okay. Do they have the same hypotenuse length? That's the longest side. Is their longest side the same length? And is there one pair of congruent legs? Okay, so that's what the three questions you need to be able to answer yes to in order to use HL. So this one is just saying, are they congruent? Are the two triangles congruent? If so, we're going to write the congruent statement. In this triangle, in these triangles, number one, we have two right angles, so we do have right triangles, so we can go and check, are the hypotenuse the same length? Since those are both 10, that's awesome. We have our first two questions answered, and then third, do we have one pair of congruent legs? And we do, since 6 is the same as 6. So this one, we're going to say, yes, they are congruent, so we're going to write that congruent statement, and I might write A, B, C, and then see what that's congruent to this time. That would be D, E, F in corresponding order. We're going to say by hypotenuse leg or by Theorem 4-6, but we usually just call it hypotenuse leg. Moving on to the second one, the first question is whether or not they are right triangles. Over here we know yes they are, or this one on the right is. By vertical angles, I could put a box on this one. So these are right triangles with congruent hypotenuse. Remember, the hypotenuse is found opposite the right angle. And one pair of congruent legs as well. So we have everything we need to say that triangle LMP is congruent to triangle OMN by HL. They have to be right triangles. They have to have a congruent pair of hypotenuse and a congruent pair of legs. Okay, moving on to this one, if you think about question 1, do we know that T and Q are right angles? We want to know if we can say that. Well, without a given or anything like that, we can't just assume that those are right angles, which means we're going to have to say no, they're not congruent. We don't know any right angles. Without right angles, we cannot use HL. Okay, last one. With the right angles here, X and T, we can move on to question 2. The hypotenuse is this shared side, which by reflexive property is congruent to itself. So we have a pair of hypotenuse that are the same and a pair of legs that are the same. So this one we can say we can use HL for. That would be RVX congruent to RVT by hypotenuse leg. Moving on to something different then. So this one says, for what values of X and Y are the triangles congruent by HL? So we already know that they're right triangles in both of these situations. What they want to know is what X has to be and what Y has to be in order for us to say yes, that these are congruent by HL. So what we know is the hypotenuse pair has to be congruent. So I know that this hypotenuse has to be equal to this hypotenuse. The hypotenuse is opposite the right angle. So that means I have one equation that I can set up as X equaling to Y. I also know that these legs have to be congruent. X minus 4 would have to be congruent to the Y plus 3. So X minus 4 equal to Y plus 3. All right? So in both of these equations, I have a system of equations right here. All right? In both of them, I don't have an equation that has just one variable. Both equations have x and y in it. So we can solve this by substitution, which is something that was discussed in the first video. What that means is if I have a letter all by itself, like x, anywhere I see x in the lower equation, the blue equation, I can replace it with 2y. So that's exactly what I'm going to do for my first step here. Since x is all alone, I'm going to just replace it or substitute 2y instead of x. And now I have something that I can solve since that is only one variable. So I can add 4 to both sides, I can subtract y from both sides, and I end up with my answer of y equals 7. Now that I know y equals 7, I can plug it in to something that is easy to plug into, such as the 2y up top. I know that if x is 7, or y is 7, I can plug y in to find x. That means x is equal to 2 times 7 instead of y, or x is equal to 14. So that's why we brought up systems of equations in the first video, because we might need them to solve our specific types of triangles that we have here. All right, then moving on. Same exact type of problem here. I know that the hypotenuse pair has to be congruent. That's y plus 5 equal to 2y minus x. I also need the pair of legs to be congruent. That's y plus x equal to x plus 7. So I'm going to write that part down. Again, this is something that is not easy to solve the way it is right now. Because this is a system of equations where I don't have anything where I have a letter all by itself or only one letter in the equation. So in this situation, I'm not ready to substitute quite yet since I don't know which letter I should isolate yet. But something nice happens to us here. If I try to get this y all by itself, I would have to subtract x from both sides. And what happens there to change that equation is the x's will drop right out of this equation. Meaning, if I solve that one for y, I already get my y value. Then I can take that y being 7 and I can plug it into that top blue equation. So instead of y, I'm going to write 7 plus 5 equals 2 times 7 minus x, and I'm looking for x this time. So on this side, I have a 12. 2 times 7 giving me 14. If I subtract both sides by 14, I end up with negative 2. But that's equal to negative x, which means if I divide both sides by negative 1, I know that 2 will be my x value. I can check all of these answers by plugging in. So if I know that y is 7 and that x is 2, I can do 7 plus 5 here and get 12. Over here, I have 2 times 7, which is 14, minus x is 2, which is also 12. All right, so that one checks out. On the bottom side here, I have 7 plus 2, or that's going to be 9. Over here, I have 2 plus 7, which is also 9. So I can plug into my original equations and see what works. Okay, so that's using a system of equations to solve for that missing variables. Maybe there's more than one. Okay, all right, and then we'll go and talk about the proofs. All right, in this proof, what I have is that I have a given with a few different things in it that's going to help me to try to build towards being able to use HL. Now that we know so many ways to prove things, there might be other ways to do this one, but to use HL, I have to do a specific order here, and that's what I'm going to try to do. All right, so let's start with making our T-chart, and we can start to copy down those givens. So we have BE that bisects AD at C. Okay. We also have that AB is perpendicular to BC. We have DE perpendicular to EC. And then we have one pair of sides that are given to us as congruent. AB is congruent to DE. All of those things are marked on the picture. So if I'm thinking about the HL theorem, I need right triangles first off. Then I need a congruent pair of hypotenuse and a congruent pair of legs. They gave me a congruent pair of legs. That one is done. So I need to say two things in my proof. I need to say why the triangles are right triangles. And then I need to say why the hypotenuse pair have to be congruent. So that's what we're going to try to do with this proof. Step 2, we're going to use all this perpendicular business here to show that angle B and angle E are right angles. The reason I know that those are right angles is that I have the term perpendicular in my given. So just because I see the word perpendicular, that allows me to use definition of perpendicular as a reason for my proof. Okay? The reason that I want to say that they're right angles is so that I can say that the triangles are right triangles. Triangle ABC and triangle DEC are right triangles then. The reason they're right triangles is the definition by definition. So definition of right triangle. Right triangles have one right angle each. So I just proved that there's a right angle in both of those triangles. So back to the picture, I have two of the three things I need. I have a pair of right triangles with a pair of congruent legs. I need to say that this pair of sides, this pair of hypotenuse has to also be congruent. So I need to say AC has to be congruent to CD. And that comes from the bisect. I haven't used the bisect step yet. I know that BE is cutting AD in half at C. So C is acting like a midpoint, in other words. I know that AC has to be congruent to DC. They're a pretty good band. You can look them up. AC is congruent to DC because of that word bisector. I'm going to write definition of bisector. Anytime the word bisect pops up in the given, we're going to use definition of bisector as a reason in the proof. And then now I have everything I need to satisfy HL. I have a pair of congruent legs, a pair of congruent H's, hypotenuse, and a pair of right triangles. So I can say, to finish up, triangle ABC is congruent to triangle DEC. And the reason being is the HL theorem. So that would be a proof using HL. We probably could have done something with the vertical angles instead and used maybe AAS or something like that. But that's about it for HL. Use this with the first video. Make sure everything's making sense. Feel free to rewatch anything like the system of equations, algebra problems I was working through. And good luck on the worksheet. Thanks for watching.